Well, here we have three factoring problems to resolve. So, first, we have to find all the natural numbers that can replace b and make the expression 5x squared plus bx minus 9 factorable. Now, the natural numbers are 1, 2, 3, 4, and so on. Natural numbers are positive, so b must be positive. So, first case, if this factors, we're going to have two sets of parentheses, and the factors of 5x squared are 5x and x. Now, here are the factors of 9, and we'll choose the factors 1 and 9. Next question. Which of these factors gets the positive? Well, since the middle term's positive, we'll assign the positive to the largest of the factors, 1 or 9, and so 9 will get the positive. And because the first and last signs disagree in the expression, we know these two signs will disagree, so we need a negative here. Now we know that 5x times x is 5x squared, and negative 1 times 9 is negative 9. So our interest is in the middle term. To produce that, we'll multiply the inside times inside. Negative 1 times x is negative x, and outside times outside, and 5x times 9 is 45x. And when we sum those, we get a difference of 44x. 44 is positive, so b equals 44. It's a natural number. Had we switched the signs, we would have wound up with a negative 44, and negative 44 is not a natural number, so that would not do. But we've done it right. Now, let's try another case. And there's our parentheses. Factors of 5x squared are 5x and x. And now let's switch the positions of 1 and 9, but let's maintain a positive on the 9 and a negative on the 1. Now, we already know the product of the two first terms is 5x squared, and the final term, the product of the final terms is negative 9. So we want to check the product of the inside terms, which is 9x, and the outside terms, which is negative 5x. And this sum, which is a difference, gives us 4x. And 4 is a natural number, so b equals 4 in this case. Finally, one more case. There's our parentheses, 5x and x. This time we'll choose the factors of 9, 3, and 3. And so the issue is, which one of these 3's gets the positive? Well, let's look at the product of 5x and 3. And that's 15x. And then let's look at the product of 3 and x, and that's 3x. Well, clearly, if this 3 was negative, we'd have a negative 15 here, and the difference would be negative, and that would not be a natural number. So this sign must be positive, and by default, this negative. And negative 3 times x is negative 3x, so when we sum these, we get a difference of 12x. 12 is positive, so in this case, b equals 12. And so, the natural numbers that make the expression 5x squared plus bx minus 9 factorable are b equals 4, 12, or 44. And we're done. Well, we have two factoring problems yet to complete. And the principle we're working with relative to these two problems is called the difference of two squares. And the difference of two squares, perfect squares, always factors in this manner. Where you have a squared minus b squared, that will equal the quantity a minus b times the quantity a plus b. So here's our expression. The first step is factor out any common factors. So 4 is common to both terms, as is x. So we get 4x times 1 minus 4x squared. Now, 1 is a perfect square, and 4x squared is a perfect square, so it will fit this criteria. So we need two sets of parentheses. We're going to put a minus sign and a plus sign. What's the square root of 1? It's 1. What's the square root of 4x squared? Well, it's 2x. And 2x, and we are done. Now let's look at the next one. And that expression, by the way, this was 2, and now we'll do 3. And that expression is 2a minus b quantity squared minus c squared. And you'll notice these are two perfect squares. So it must fit the criteria of the difference of two squares. So to distinguish brackets and parentheses, I'll use a bracket here and bracket, bracket, bracket. And now inside we'll have parentheses, and we have 2a minus b minus c and 2a minus b plus c. And now we can dispense with these parentheses. So this is inside, and just use parentheses throughout. So we get 2a minus b minus c and 2a minus b plus c, and we're done.